So, okay, now I think it's already time to start our lecture. So, Laura, could you please share your screen? And meanwhile, I welcome everybody at our 13th lecture. It will be given by Laura Kreidberg. She's a director of Max Planck Institute for Astronomy, and she will be given a lecture on one of the hottest topics in astronomy today about exoplanets. So, Laura, the floor is yours, please.
All right, thank you very much. It's really a pleasure to be speaking with you all this afternoon, this morning, whatever time zone you're in. My name is Laura Kreidberg. I'm the director of the Atmospheric Physics of Exoplanets department here at the Max Planck Institute for Astronomy in Heidelberg. And before I get started with the science, I wanted to give just one slide of advertisement for this department that's relevant for all of you because we are hiring. So we are a relatively new department founded in 2020. And the focus of the work that we do here at MPIA is observations, theoretical models, even instrumentation, all related to the topic of exoplanet atmospheres. The department is growing rapidly. This is a snapshot on the bottom right of what we look like at the moment. In fact, this is already a little out of date. But we are hiring at all levels, so PhD, postdoc, even staff position. And so if this is a topic that interests you or is something that you're working on, your friends are working on, please keep an eye out for job advertisements. We advertise more senior positions on the AAS job register, and PhD positions you can apply through the MPIA website. Okay. Good. So why do we care about chemistry in exoplanet atmospheres? There's a lot of reasons, and I listed a couple of them here. One big one is that by studying the present day chemistry of an exoplanet atmosphere, we can learn a lot about the origins of the planet, how it formed, how it evolved and changed over time. We think that atmospheres are dynamic, they can be lost over billions of years. And ultimately, the really big question that motivates myself and many others in this field is to use the chemistry of the atmosphere as a tool to learn about the habitability or even whether a planet is inhabited. So a brief overview of topics for today. There's tons and tons that we can talk about, so I tried to break it down, starting first with a little bit of background about how we actually study the chemistry of exoplanet atmospheres. I remember when I started as a PhD student, it was right when the Kepler spacecraft had first launched, and so there were a lot of discoveries of new planets. And at the time, I was super uninterested in working on exoplanets because it was a really popular topic, and I thought everyone else was doing it, and there was nothing useful that I could contribute. But then I learned that it might be possible to study the atmospheric chemistry, and that seemed to me like a much more challenging topic that would give a really long runway of exciting work to do over decades and decades. And that has, in fact, proven to be exactly the case. So I'll start a little bit about how we actually do this type of measurement in practice. Then I'll give a short overview of what we have learned about the chemical composition of gaseous planets, both Jupiter-sized planets and pushing down to even sub-Neptune size. I'll move on to a very important topic, which is clouds and hazes. And finally, I'll wrap up with some perspective on what we can learn about the chemistry of rocky planet atmospheres, both now and in the future. Okay, so first things first, measuring atmospheric chemistry of exoplanets is very challenging. The ideal scenario would be one like this one, where we can spatially separate the planets from their stars on the plane of the sky. However, there are two big challenges. One of them is that planets are much fainter than their stars, at least least 10,000 times, often even fainter as you push to more mature planets or smaller planets. And not only that, but planets and stars are also very close together on the sky. And so this direct imaging technique where you can just block out the light from the star and image or take spectra of the planets orbiting it is only possible for a small sample of planets, something like a couple dozen planets that are bright enough and widely separated enough that you can easily take a picture like this. So fortunately for us, there's another approach that we can take, which is to observe transiting exoplanets. And so even though we can't, for most systems, spatially separate the planet from the star, what we can do is measure the total brightness of the system over time. And of course, this is a transit. So as the planet passes in front of the star, a little bit of the starlight is blocked, something like 1% for a Jupiter-sized planet around the sun, less for smaller planets. And we can use this to study the atmospheric properties of the planet. And the way this works is the following. So during a transit, when the planet is in front of the star along our line of sight, the starlight will filter through the planet's atmosphere where it can be absorbed or scattered by atoms or molecules or cloud or haze particles. And so at wavelengths where the atmosphere is more opaque, the planet appears slightly larger. And so that manifests as a larger transit depth. To make this a little bit more intuitive, I have an example here of the Earth as imaged from space. You can see the moon in the background there for scale. And then I drew an arrow to the atmosphere of Earth. You can see it because of the blue Rayleigh scattering signature in optical light. But if you move instead to the infrared, that's what the Earth looks like. So you can see if I go back and forth between these, that the Earth appears to be a little bit smaller, and that's because of the absence of this Rayleigh scattering at longer wavelengths. But if you move just a little bit redder, the Earth appears larger again, and this is because between 9 and 10 microns, there's a strong absorption band from ozone. And so what you're seeing here is the higher ozone opacity increases the apparent size of the Earth. From a perspective like this, it's really, really easy to see the difference between these scenarios. Of course, it goes without saying that if it's easy to do this if you're orbiting the Earth, you're right next to it. If you're trying to make a similar measurement for an Earth analog around a star that's 20 parsecs away, we're talking about a much, much different level of difficulty, but not impossible. Okay. So this is a cartoon of a transmission spectrum for a planet. So this is showing planet radius versus wavelength for a cartoon absorber. I think in this case, this was a pure water atmosphere for our toy model. And in contrast to most types of spectroscopy, absorption is up because when the opacity is higher, the planet's effective radius, is a little bit larger. And so the key to measuring atmospheric chemistry is to compare the size of the planet versus wavelength to our knowledge of different opacity sources from both theoretical calculations and also lab data. And we can use that to work together to learn what the chemistry in the atmosphere is. So similarly, transits are one of the most common ways to study the chemistry of exoplanet atmospheres. But another common technique that I like a lot is to observe the planet as it passes behind the star. And the idea here is that when the planet is eclipsed by the star, any of the light emerging from the planet, whether that's thermal radiation or reflected light, is blocked by the star. And so you can use this to measure both a thermal emission spectrum or a reflectance spectrum in the optical. And finally, my most favorite approach for studying the chemistry of exoplanets is to observe what's called the thermal phase curve. And this is only possible for short period planets that don't take that long to orbit their stars. But the key idea is that you can stare at a planet over a complete orbital revolution, so an entire revolution around its star. And for these short period planets, they're tidally locked. And so there's a permanent hot day side and a permanent cold night side. And as the planet moves through its orbit, the viewing angle changes. And so you're exposed to different regions of the atmosphere over time. And you can use this to make an actual global map of the chemistry, the atmospheric composition, but also the temperature structure. So this is a really powerful method for learning more about exoplanet atmospheres. Okay. So it this sounds kind of obvious. It goes without saying that studying the atmospheres of other worlds is easier when Earth's atmosphere is not in our way. And so for this reason, the workhorse facilities, the telescopes that have been used the most for exoplanet characterization have been space telescopes. Spitzer and Hubble were the key players for a very long time. And then a couple of years ago, we fortunately had the launch of JWST, which has been a complete game changer for exoplanet atmosphere studies, as I'll talk more about in the lecture. Sorry, I hear some background noise from outside. I'm going to close my window so that that doesn't disturb us. 1 second. It's a sunny day here in Heidelberg, so I was trying to enjoy some of the nice weather. But okay, good. So space-based observatories have been some of the most powerful for studying exoplanets. That has been a lot of the focus of my own research activities. But I also want to emphasize that it is possible to do this from the ground if you are clever enough. And so one of the ways that we can outsmart Earth's atmosphere is to observe exoplanets at very high spectral resolution, where you can actually resolve individual absorption lines in the planet's atmosphere. And I have a little animation to illustrate how this works. So as the planet orbits its star, its spectrum is Doppler shifted, its red shifted is moving away, and now as it comes back around, the spectrum is blue shifted. And so the exoplanet spectrum is shifting in a predictable way based on Kepler's laws compared to the stellar lines and also Earth's atmosphere absorption, the telluric lines, which are approximately fixed over time, or at least not varying with wavelength in the same way that the planet lines are. And this is a technique that is very complementary to the work that can be done from space. There's no very high resolution spectrographs in space because they're simply too big to be practical at the moment. So there's now quite a lot of ground-based instruments that are doing this type of high resolution characterization. CRIRES on the VLT was the first one, but then we've moved on to many others that I've listed on the slide. And there's a couple of advantages to this approach. One of them is that you can actually measure the shape of the line, which tells you something about the atmospheric dynamics. You can look for the broadening of the line. That might tell you about the planet's rotation speed. And in addition to that, it's also possible to search for rarer species that have weaker lines or fewer lines that at low resolution would be totally swamped by the lines from the dominant absorbers like water or methane or things like that. So I think this is a really powerful complementary technique to what is possible from space. And in addition to that, of course, it's also possible for some cases to directly image the planets. Here's this nice animation, again, showing the famous HR 8799 planets orbiting their star. So this direct imaging technique is really on the rise. We're pushing towards the next generation of instrumentation that can make these measurements for planets close to where we think the peak of gas giant planet occurrence is. We're not quite there yet, but this is the goal in the relatively near future. And very recently, it also became possible to detect planets with optical interferometry. So this is a great result from the gravity instrument on VLTI, where thanks to the very, very long baseline interferometry, it's actually possible to spatially separate the planet from the star. Okay. So, a little bit of history for you. Now we know that it's possible to detect atmospheres on exoplanets, but in the very early days of the field, not much more than 20 years ago, there were some serious doubts about whether atmosphere characterization was possible at all. And the idea was first proposed by Dave Charbonneau, who many of you know discovered the very first transiting exoplanet. And in his discovery paper, he wrote a few lines saying, yeah, you might be able to observe the planet as it passes in front of the star, and measure the wavelength dependence of the transit depth and learn about the atmosphere. And got the referee report back, and they were so skeptical. The referee said, oh, like, what kind of a telescope do you think you could use to make a measurement like this? You have to have really precise data, blah, blah, blah. And so then, of course, a couple years later, Dave Charbonneau just went ahead and did this. This is the very first detection of an exoplanet atmosphere. This was for a hot Jupiter called HD 209458b. It's one of the brightest and easiest to observe hot Jupiters in the sky. They used the Hubble Space Telescope all the way back then to measure the size of the planet in and out of the sodium, the sodium doublet. And you can see on the left here, the bottom panel is showing the second half of the transit, and you can see that starting from 0, that's the central transit, the planet is a little bit larger than it is outside of transit. And so this was a few tenths of a percent amplitude signal, so really small signal, but highly significant, greater than 3 sigma detection. Okay, so that is some background for you about how we actually do this. So I'm going to move on now to some of the scientific questions and what we can actually learn about exoplanet atmosphere chemistry. So I mentioned at the beginning that one of the questions we care about is the how the planets formed. And the thinking is that depending on if you're creating a gas giant planet, which dominates your planetary system by mass, the chemical composition of the planet is sensitive to the properties in the disk where it formed. This cartoon on the left here is illustrating this idea. It's a lot more complicated than this in practice, but this is just to give you a feeling for the idea. This plot is showing the ratio of carbon to oxygen in gaseous material versus solid material in the disk. And the idea is that as you move away from the star, the temperature drops, and you have freeze out of different molecules, starting with water at a couple of AU away from the host star, moving on to CO2 and then CO. And as you hit these successive ice lines, the gas becomes preferentially enriched in carbon, and the solid material becomes preferentially enriched in oxygen. And of course, there's a lot of assumptions that go into this. It depends on exactly when the planet is forming. It depends on the structure of the disk. It depends on, chemical transport within the disk. And so all of these things I'm sweeping under the rug for now. But the point is that this idea has motivated a lot of study of the chemical composition of gas giants. So when we talk about exoplanet chemistry, this is some of the terminology that we use. We often talk about elements based on their condensation temperature. So for us, gases are hydrogen and helium. Volatiles are typically carbon, nitrogen, and oxygen-bearing species, potentially sulfur as well. For exoplanets, these are most often seen in molecular form. So we're talking about things like water, CO, methane, ammonia, things like that. We also sometimes call these ices since they are often in the form of high pressure ices in the solar system. Then refractory material would be iron and silicate, so rocks that at typical planetary temperatures are in solid form. Although for some exoplanets, they're hot enough that you actually can see gas phase iron and silicon, which is pretty crazy. We also, as shorthand, talk about metallicity of exoplanet atmospheres, just the same way as you would for a star. So we talk about Fe/H. We're often referring to metallicity relative to the solar value. So you'll hear people talk about like a 10 times solar atmospheric composition or 100 times solar. The way you actually do this in practice is that you might say, well, the sun doesn't have any water in it, but you could take a solar composition gas and cool it to the temperatures that we see on exoplanets, and then use that as your base for solar composition. And if you have excess carbon, nitrogen, or oxygen, that's what we would consider an enhanced metallicity exoplanet atmosphere. And then finally, we often talk about elemental abundance ratios, particularly the carbon to oxygen ratio, as I mentioned on the previous slide, but also carbon to hydrogen, oxygen to hydrogen. Ideally, we would measure all of these to get a complete chemical census for the exoplanet. So one of the really fun things about exoplanets is that we're just in the very earliest days of studying them. And so a useful starting point for a first guess of what the atmosphere should look like is simply chemical equilibrium. So the abundances of different molecules that you get based on Gibbs free energy minimization. You guys are all hopefully learning about this in school. And it is an open question whether exoplanet atmospheres actually are in equilibrium or not. Spoiler alert, they are not in equilibrium, but nevertheless, this gives us some rough idea of what molecules we should expect or could go looking for. So the second question is not only what molecules are there, but which ones we can actually see. And the ones that we're most sensitive to are not necessarily the most abundant, but rather the ones that are the most spectrally active, so the greatest number of absorption lines. CO is really popular because we understand the absorption spectrum really well. We know where these transitions are. The number of lines is like, there's a lot of lines, but not too many. So it provides a nice feature for us to see, but also one that's easy to interpret. So by contrast, something like H2 has very little absorption signature. There's collisionally induced absorption that does shape the slope of the spectrum somewhat, but it's not going to be a nice big molecular band that we can easily identify. And so even though for a lot of these atmospheres, hydrogen or helium are the dominating atoms, those are not the molecules that we see in our spectrum. Here are some nice plots showing which molecules you would see the most easily for different assumptions about the temperature. So on the left, this is a typical hot Jupiter scenario with a temperature of about 1500 Kelvin, a pressure level of about 1/3 of a bar, and a solar metallicity chemical composition. The different colored lines correspond to the opacity times the mixing ratio. So this is sort of a shortcut guess for which absorbers are the easiest to see. And on the left here, you can see that most of the spectrum is dominated by absorption features from water. That's the blue line. There's a big peak from carbon monoxide, close to 5 microns. You can see potassium in gray towards the left-hand side of the plot, You can also see the red edge of the sodium, really broad wing of sodium there. These plots cut off at 0.6 microns because that's the shortest wavelength that JWST can cover. That's why they look like this. And yeah, but for the hotter case on the left, most of the other molecules that might be there, like ammonia or CH4 or H2S, are simply not abundant enough or not spectrally active enough to be easily visible. If instead you move to colder temperatures, you would get a fairly different plot. That's what was shown here on the right. So this is pushing the temperature down from 1500 Kelvin all the way to 500 Kelvin. 500 Kelvin is a really typical temperature for, say, like a sub-Neptune. There's a lot of planets that are kind of this warm, but not as hot as a hot Jupiter. And you can see that there's still a lot of absorption features from water. That's again shown in blue. But you can also see some other exciting species start to pop up. So you would expect methane and red to be dominant at some wavelengths. You'd see a little bit of, oh, that's interesting. It looks like pH3 in black. That's something we have not, to my knowledge, seen yet. That's a cool prediction. NH3, so ammonia, should have some really nice absorption features as you push farther into the infrared, so out beyond 10 microns. But this gives you an idea of the rough parameter space of what is possible. So most of these things are simple molecules, carbon, nitrogen, oxygen dominated. But this is also really exciting because these atoms, the carbon, nitrogen, oxygen, are the key building blocks for planet formation. And in contrast to, say, Jupiter and our own solar system, Jupiter is so cold that some of these key species, like water, for example, have frozen out of the observable part of the atmosphere. And so the water abundance of Jupiter is still relatively poorly constrained simply because it has condensed in the deeper layers that are harder to access. Okay, so how do you actually connect the spectrum of a planet that you observe to the underlying chemistry? I have a very simple toy model for you here to illustrate how we do this. We typically use a technique called atmospheric retrieval, where we compare a spectrum like what is measured on the bottom with simple one-dimensional models that can be run quickly that explore a big parameter space of different opacities and different temperature structures. So in this toy model, there's a region of higher opacity noted by this orange diamond that corresponds to an absorption feature here. This would be like a thermal emission spectrum, so not a transmission spectrum. If you change the temperature structure, so you have a thermal inversion where the temperature increases with altitude, that can happen if you have some high altitude absorber that is absorbing a lot of optical light and heating up the upper layers. And so in that case, you get an emission feature in your spectrum rather than absorption. You could add a second absorber here, and you get two different absorption features. Here's what it would look like in thermal emission, where depending exactly on the temperature structure, that sets the amplitude and size of the features. And so this is just a simple example, but the idea behind atmospheric retrieval is that you can systematically explore a very large parameter space, looking at many, many different absorbers. You can inform your models based on chemical equilibrium, which absorbers you put in. You can have a flexible temperature structure. You can also put in things like clouds and hazes. You can also try to incorporate some simple 2D effects. But this is the basic idea. You go from measured spectrum to underlying chemical composition with uncertainties using atmospheric retrieval as a tool. Okay. Good. All right, so here's a real spectrum. You stuck with me for 30 minutes. I thought I should probably show you some real data by now. So this is some observations from Hubble of a hot Jupiter. This is work that I did as a grad student about 10 years ago now. And you can see a beautiful water absorption feature, both in the emission spectrum of the planet, that's the top left, and in the transmission spectrum of the planet, that's the bottom left. And just as a reminder, for the transmission spectrum, the water absorption is up because the planet is larger, where water is more opaque. And so this was super exciting at the time. Hubble was not designed to observe exoplanet atmospheres. The host stars are way too bright, and so we had to really modify the observing strategies that are used in order to not saturate the detector. But around this time was when it first got started working. These spectra are really beautiful. I remember where I was when I measured this. Actually, I was on an airplane. I think I was going to a conference and I was working on my data analysis, and I was being so careful to make sure every step of it was believable and correct before I looked at the spectrum. And then finally I got to the airplane and I put the final touches on my analysis, and I thought, okay, this is ready. I can look at it now. And I plotted it up and I saw it just like clear as day, this beautiful water feature. And I was so excited. The poor person sitting next to me was like, are you okay? Is something wrong? I was like, no, I just discovered water on another planet. It was awesome. And now, of course, this seems a little bit cute. Like you'll see in a couple of slides that we've moved well ahead from this type of measurement. But what this allowed us to do for the first time is really reliably retrieve the water abundance in the atmosphere. And we found for this case that the water abundance is pretty close to solar composition. And if we compare that to the solar system, the metallicity of the solar system planets, we find that our exoplanet falls beautifully in line with this solar system trend. We know that the ice giants, for example, are more enriched in metals. That's why they're called ice giants. They've got more water in their bulk. And then moving towards more massive planets, those atmospheres are more dilute with hydrogen. And so WASP-43b, this exoplanet, at about 2 Jupiter masses, was very close to solar enrichment of water, which matched roughly our expectations. Then, 5 years ahead, this similar type of measurement had been done for a sample of more than a dozen hot Jupiters, showing on the right the updated plot of metallicity relative to solar composition versus planet mass. And you can see that, as is typical for exoplanets, they're much more diverse than the solar system. There's some hints here that the water abundances are subsolar, so even less water than you would expect for a solar composition gas. That was pretty controversial because that's not, normally we would expect planets as they form to be accreting either ice-rich planetesimals, or you could also be accreting water vapor that has sublimated from icy pebbles. There's a lot of ways to get water into your planet, not as many ways to keep water out of your planet. So this is kind of a surprising result that motivated some a lot of theoretical work, including some work from the group of Bertrand Bitsch, where they proposed a model where you could quite naturally get a dry, water-poor atmosphere of a gas giant if your planet is forming out beyond the water ice line, where the gas is dry, the pebbles are wet because the ice is condensed onto them. And if you're creating mostly gas and not a lot of pebbles, you could get a water-poor atmosphere. And this brought us all the way up to 2021. So this was kind of the state of the art at the time. We had about a dozen surely less than 20 low resolution space-based spectra. A lot of them showed evidence for water vapor. First results were showing possibly some water depletion, although with spectra like this, as beautiful as I thought this was, it's pretty limited wavelength range with fairly large error bars. And you can see that the inference of the water abundance has a pretty wide range that I think reflects the quality of the data. So, okay, but we made some progress. Then JWST launched, and this was such a big deal. I almost couldn't watch the launch because I was so nervous that there would be a problem. So why were we so excited about JWST? There's a lot of reasons. First of all, it has a much larger mirror than Hubble does, so it's about 10 times larger collecting area. But not only that, it has much broader wavelength coverage, which opens us up to detecting all kinds of molecules that were just inaccessible with the limited wavelength range of HST. In particular, one of JWST's most special features is its infrared capability. You can see here in the animation, the sun shield is starting to unfold. This for me was the scariest part because this thing is so thin. It had to be perfect to effectively block out there it is. There's the tension put on the sun shield that blocks out the heat from our own sun, and allows us to observe things all the way out to 30 microns or so long wavelengths, in very cold temperatures so that we're not dominated by thermal background. And there it goes. The primary mirror is almost finished unfolding. There it is. All right, done. Easy peasy. Okay, so one of the first things that JWST observed was a hot Saturn called WASP-39b. This planet was observed by the Transiting Exoplanet Community Early Release Science Team. That's a kind of a mouthful, but it represents a very large number of people, hundreds of people participating in an open program internationally. And the goal of this early release science was to test JWST's performance for exoplanet spectroscopy early on in the mission so that we could learn how it was working, and make the best use of the telescope during its lifetime. So here is what the spectrum of WASP-39b looked like between 3 and 5 microns previous to 2022. This is some Spitzer data from Hannah Wakeford. And you can see with JWST, that's our new spectrum. Look at that. This does not get old. I've seen this like 5 million times and I still think it's cool. There it is. That's CO2. So that huge absorption feature between 4 and 4.5 microns is carbon dioxide, the first time it was detected ever in an exoplanet. Okay. And that is not all. So as part of this program, we built a panchromatic transmission spectrum. This is results from the NIRSpec prism, which gives a straight shot from 0.6 all the way out to greater than 5 microns. And you can see the different colors correspond to all the different opacity sources that are shaping the spectrum that we see. So as I mentioned, that huge peak, a little bit redder than 4 microns, that's carbon dioxide. You can also see a whole bunch of absorption features from water. You can see sodium. You can see carbon monoxide. And this data is so new. You can see all of these references on the slider from 2023. We're still in the process of interpreting exactly what this means for the overall atmospheric chemistry. But I can say, just as kind of a rule of thumb, if you see carbon dioxide in your planet atmosphere, that almost certainly means that you have some significant enhancement in metals relative to the solar value. So I would say if you see CO2, that points towards something like at least 10 times solar metallicity. And the reason for that is pretty simple. If you have more carbons and oxygens floating around, they're more likely to favor a molecule that has 3 of these heavier atoms as opposed to H2O or CO or CH4. The more carbons and oxygens you have, the more likely you are to favor CO2. So there's a huge modeling effort that has been going on for months now to try to combine and synthesize all of these data and very precisely measure the enhancement of carbon relative to hydrogen, oxygen, and sodium, some of these other species. But I think it's going to take some time to get an answer that we really believe. And this didn't come as a surprise, right? I think we knew as a community that data of this quality would really push our theoretical models to be much more sophisticated than they were at the launch of JWST. And indeed, that's what we're finding, is that actually combining all of these data into one consistent picture is taking some time. Okay, so some of the other part of the reason this is taking so long is that as soon as we see an atmosphere in this level of detail, we're also exposed to some of the chemical complexity that is going on. In particular, for this planet, there is photochemistry going on, and that is causing this little additional absorber right at 4 microns. You can see that little bump right at 4 microns. Actually, the previous slide is a bit better. You can see that little red bump right at 4 microns. That is sulfur dioxide. And that came as a big surprise to all of the naive astronomers, including myself, who were focused on equilibrium chemistry. Because in chemical equilibrium, SO2 is not expected at these temperatures and pressures. But if you talk to anyone who is an expert in photochemistry, they say, of course, like, here's my elaborate chemical network where you photolyze water and then the hydrogens react with H2S, and you have this complicated network illustrated on the right here that eventually will produce sulfur dioxide in large enough abundance that we can detect it. And so this was pretty exciting. This is, like, we know that photochemistry has really shaped the atmospheres of the solar system planets, but we had never definitively detected photochemical products in an exoplanet atmosphere before. And it looks like WASP 3090 is not the only case where this is true. SO2 has been detected in a number of other planets, almost at the level now where people are like, oh yeah, that's SO2. Like, of course there's SO2, which is so funny to me because you know, not much more than a year ago, we were scratching our heads trying to figure out what that bump was, and everyone was arguing about it. We had no idea. And now it's like, oh yeah, SO2, like, duh, of course it's there. So this is a fun reminder of how fast science can sometimes progress. Here is, oh, sorry, I'm getting a phone call. I don't know, probably not so important. So, okay, I wanted to share another very exciting spectrum that is brand new. This paper came out just last week, so it's almost barely enough time for me to like read the paper and digest it, but I still wanted to share it with you. So this is the transmission spectrum of a smaller and cooler planet called TOI 270d. This planet is, in the whole spectrum of planets, much closer to the Earth. So it's only about 2.2 times the radius of the Earth. I forget exactly the temperature, but it's definitely below 500 Kelvin. So it's pushing closer and closer to the habitable zone. And this is the spectrum that was published just last week. Look at that. You can see a whole bunch of absorption features from methane. I'm counting 1, 2, 3, 4, 5 big absorption bands. A little bit of water poking out too, that's the blue. And then, really excitingly, this this turquoise color corresponds to opacity from CS2, which again was not expected. This is a photochemical byproduct that was on nobody's radar except the poor photochemical experts who've been, banging away at these problems for years, and now finally the rest of us are listening. So this was really exciting. This also showed not only is there photochemistry, there's also most likely vigorous vertical mixing that pushes the chemistry out of equilibrium. At these temperatures, we expected to see some ammonia. The ammonia is not there, which suggests that the chemistry is being quenched at deeper pressures, higher temperatures. And finally, putting all of this together, the chemical composition of the atmosphere overall was found to be quite enriched in metals. So metal mass fraction near 50%. That corresponds to a mean molecular weight of about 5 AMU, so roughly hydrogen, molecular hydrogen would be 2, water would be 18. So this is showing that there's a lot of water and methane and CO2, CS2, even that are polluting the atmosphere to increase the mean molecular weight. And this is something that the field has been waiting to measure for a really long time. This is a fundamentally different type of planet than anything in the solar system. We have none of these sub-Neptunes, so nothing intermediate between the Earth and Neptune in size. So I think this, the spectrum just came out last week. There's a lot of work left to do to interpret it, but I just thought this was so exciting. I wanted to share it with all of you today. Okay, good. So I want to move on to another type of chemistry in exoplanet atmospheres, which is clouds. We know that in the solar system, clouds and hazes are extremely important. It's the one thing that every planet with a substantial atmosphere has in common. So there's the sulfuric acid clouds on Venus, we have water clouds on Earth, ammonia clouds in Jupiter, as well as photochemical hazes that are responsible for those rich brown colors. We even see evidence for hazes in the atmosphere of Pluto. I don't know if you can see this at the resolution of your computer screens, but in the bottom right, this is that stunning image of Pluto taken by the New Horizons mission, and you can see layers in the atmosphere caused by different photochemical hazes. And so we know that over this very broad range of temperatures, a broad range of chemical compositions, we see clouds and hazes in every single solar system planet with a thick atmosphere. And we expect to see clouds and hazes for exoplanets too. And similar to just the overall chemistry, we can turn to chemical equilibrium as a rough guideline of what to expect. Here are some model condensation curves for different molecules that we would expect at typical exoplanet temperatures, compared to temperature pressure profiles for a sub-Neptune on the left, or like a warm sub-Neptune on the left and a hot Jupiter on the right. So the planet temperature pressure profiles are shown with the dark black lines, and the condensation curves are shown by these colored dashed lines. And you can see on the left for this warm sub-Neptune case, the clouds would be expected in chemical equilibrium to form out of these salts and sulfides. So potassium chloride or zinc sulfide are crossing the planet's temperature pressure profile. When that crossing happens, that's when you expect the molecule to condense. So that is one possible condensate that you might expect for a planet in that temperature range. For hotter planets, for hot Jupiters, that's what's shown on the right. You can see that the temperature pressure profile is crossing condensation curves for silicate clouds, so iron clouds as well, and then Mg2SaO4, MgSaO3. Those are the most typical cloud species that we'd be expecting in hot Jupiter atmospheres. In addition to equilibrium clouds, we would also expect photochemical hazes to be forming. And there are lots of different pathways to form these hazes, but a typical one is from methane photolysis, where you have a high energy photon from the star that comes in and it breaks up your methane molecule into carbons and hydrogens that can recombine into these higher order hydrocarbons like C2H6, HCN, C4H2, that can clump together into larger and larger hydrocarbon haze particles, somewhat analogous to the hazes that are seen on Saturn's moon, Titan. The abundance of these hazes is sensitive to temperature because you would expect the most methane at temperatures below about 800 Kelvin. As you get hotter, the methane goes away, your carbon preferentially goes into CO and CO2. And so it's really for these lower temperature things below 800 Kelvin or so where these methane haze pathways are expected to be the most prevalent. Okay. We also happen to be very sensitive to clouds and hazes in the typical measurements that we make for exoplanet atmospheres. And the reason for that is that the photons through the planet's atmosphere have to traverse a very long path along their way to the observer. So here in this cartoon, the sun, or the host star is on the bottom, the observer is on the top of this figure, and the photons from the planet have to pass all the way through this long slant path through the atmosphere. That results in an optical depth for the cloud and haze particles that is between 30 and 90 times greater than the normal opacity if you're just looking straight down onto the planet. So you're comparing this distance x here for a slant geometry during transmission versus the much shorter distance z, which reaches the same optical depth for other species in the atmosphere, but produces these really much higher opacities for clouds and hazes. In practice, what happens is that if you have a model transmission spectrum that looks something like this, and you put a cloud deck at a certain altitude, the clouds tend to truncate the amplitude of spectral features at the pressure level where the clouds are present. So in this case, let's see if I did it. Yeah, there it goes. You only see these tiny little spectral features poking out above the cloud tops. In this model, this is a very simple approximation for the cloud properties, assuming that they have constant opacity with wavelength. In reality, clouds can introduce some slope. Some of them even have some spectral features, and I'll get back to that later in the lecture. Okay. So clouds have been hypothesized for exoplanet atmospheres all the way from the very beginning. So this is going back to the measurement of sodium in the atmosphere of HD 209 that I introduced at the very beginning of the lecture. And you can see here, the red bar is the measured transit depth in the sodium line compared to a couple of different models. And the, oh, I think my legend is mislabeled. I think the first and second item on there should be switched. Because for a solar composition atmosphere with a deep cloud, or one very deep in the atmosphere, you'd expect the largest features. So that's the dotted black line. But for a solar composition atmosphere with a high cloud, you get these truncated features that are shown with a solid black. And so the measured sodium strength was pretty small, about 4 times smaller than expected for a cloud-free or deep cloud solar composition atmosphere. And so the leading explanation, even then, all the way back in 2002, was that there's some type of cloud in the atmosphere that's truncating the transmission of stellar flux at the cloud deck altitude. Okay. Clouds have, in some cases, completely obliterated any trace of spectral features. And here's one famous example. This is for a sub-Neptune called GJ1214b. This is the spectrum that I'm maybe the most infamous for measuring, it's been called the most expensive flat line in astronomy. But it was a very informative one because this spectrum, these black data points, are so flat that we were able to rule out all possible high mean molecular weight compositions for this planet's atmosphere. So at the time, sub-Neptunes were, it's a 2.7 Earth radius planet. There were some theories that maybe the atmosphere was really, really water dominated, and so it would shrink the spectral features because water is heavy. But our data were so precise here that even a pure water vapor atmosphere was ruled out, as was a methane-dominated atmosphere, even CO2. And so the conclusion that we came to is that there must be clouds or hazes at high altitudes in the planet's atmosphere that are truncating the spectral features. There was also a lot of evidence early on for haze scattering slopes. Here's the optical transmission spectrum of another hot Jupiter. You can see this really strong optical scattering effect that is thought to be due to small haze particles in the upper atmosphere. This could be photochemical hazes that are producing little grains that are causing a lot of scattering. More evidence for clouds or hazes came from phase curves. This is an optical phase curve measured from Kepler for another hot Jupiter, where actually the peak brightness of the planet is happening westward of the substellar point. And the interpretation here is that, and that's backwards from what we would expect from atmospheric dynamics. We would expect an eastward shift of the hotspot, not a westward one. And so the explanation was that maybe this planet has inhomogeneous or patchy cloud coverage, where the map that you see on the right, that those dark regions have a cloud that is blanketing the planet and masking the thermal emissions, so the planet appears cooler and darker at those longitudes. Okay. Good. So I showed this spectrum already. One of the questions that we have is like, what are the clouds and hazes actually made of? How much can we learn about their properties? And for this particular example, we ran a very simple model assuming a variable cloud deck altitude with a gray cloud and also variable water abundance. And we found that the clouds have to be at about 1/10 of a millibar or lower pressure, so very, very high up in the atmosphere. Compared to Earth clouds, which are found at a couple hundred millibar, these are orders of magnitude lower pressure in the atmosphere. And so at these temperatures, this is one of the planets where we'd expect equilibrium condensates to form out of salts and sulfides. But the question is, how do you get them so high up in the atmosphere, and how do you keep them up there? And so one possible explanation was that maybe rather than having a compact spherical cloud particle, instead you could have like a fluffy aggregate that has a large surface area relative to its volume. You can form these by low speed collisions between cloud particles that produce these sort of complex, very porous cloud species that are easy to loft up and keep high in the atmosphere. So maybe that is responsible for the very flat spectrum measured for GJ1214b. Okay. Another question is, where are the clouds and hazes? I took this quote from Michael Roman, who said, maybe they're everywhere, maybe they're somewhere, maybe they're nowhere. And what motivated him to make that statement is that these are some showing on the left here some 3D models that tried to predict where in the atmosphere clouds should be forming. And he found that depending on what you assume exactly about the cloud formation process and properties, that you can get completely different results, either a completely cloud-covered planet, a clear atmosphere. And so I think that, I'm coming at this problem from an observer's standpoint, but I want to emphasize that there's also some big challenges and questions on the modeling side too, of what we should expect for the cloud and haze properties for these planets. We can also learn a lot from looking at demographics. So this is also a pre-JWST result, but I think it's a really powerful one. And this is some work from Peter Gao, who compared the measured amplitude of the water absorption feature that Hubble can measure. So the very first spectrum I showed you, that's the nice water absorption feature. This has been done now for, I don't know, something like 20 planets or so. And in this paper, Peter Gao measured the amplitude of that feature as a function of planet temperature and compared it to physically motivated microphysical cloud and haze models. And he found that he could get a pretty decent fit to the data with models that included photochemical haze formation at lower temperatures, below about 1,000 Kelvin, and silicate cloud formation for the hotter planets. And so you get this kind of multimodal prediction for how large the water features should be. At the lowest temperatures, you've got these thick hazes. Then as you move from about 1,000 to 1,700 Kelvin, you get thicker and thicker silicate clouds. And then as you get hotter, the silicate clouds actually evaporate again, and you start to approach cloud-free atmosphere. One thing to note is that while the cloudy and hazy models are not a perfect fit to the data, they are much closer than the cloud-free models, which are shown at the top there with that the dashed boundary lines. That's the prediction for the water feature amplitude for an atmosphere that has no clouds or hazes whatsoever. And so if there's any takeaway from this plot, it's that clouds and hazes are all over the place. And a model that with methane-generated hazes at lower temperatures and silicate clouds at higher temperatures does a pretty good job of explaining what we have observed. Another interesting development is that if you push towards the lowest temperatures, the clouds actually appear to go away, at least in part. And here's a really fun planet called K218b, which is actually in the habitable zone of its host star. This is not a habitable planet. It's too big to have a rocky surface, so it's really more of a closer to it, like a Neptune type of thing than an Earth. But it does give us a first opportunity to study atmospheric chemistry at temperatures similar to the Earth. And you can see this is old data from Hubble. It's now been observed with JWST, so I need to update these slides. But you can see already here beautiful absorption feature, in this case due to methane. And so we were really surprised. In fact, when this paper first came out, I didn't really believe it because I was expecting that, as I showed on this slide, as you go to lower and lower temperatures, you get more and more of these photochemical hazes. But maybe one possibility that has been inspired by work in the lab is that as you go to lower temperatures, the surface energy of the haze particles increases, which allows them to clump together and grow. And they become large enough that they get heavy and rain out of the upper atmosphere. So this is a really nice paper from Xinting Yu based on experiments she did in her lab, showing that at these moderate temperatures, kind of 400 to 500 Kelvin, you have the lowest surface energy particles that don't grow efficiently. And so those can linger high up in the atmosphere, whereas both at hotter and at lower temperatures, the particles can more efficiently grow, aggregate, get heavy, rain out and provide a nice, relatively haze-free atmosphere for us to observe. And so the big prediction from this is that perhaps when we push to more Earth-like planets, when we're really studying rocky planets in the habitable zone, that hopefully those atmospheres may be relatively free of hazes. That would be super awesome. And just as an example, because this is so cool, this is some of the results from these haze experiments in the lab. You can actually measure the color of the hazes. They're kind of brown, even like a little greenish, some white ones. Typical sizes are pretty small, so like 50 to 100 nanometers approximately. And we can even compare them to what Titan looks like. This is a picture taken by the Huygens lander, and you can see that that really sort of like brown hazy color matches almost exactly what we have seen in our own solar system. So I like to show this because one of the most common questions I get from like my family and my friends who are not astronomers is what color are the planets? And that's hard to do. Like you could in principle measure it if you had an optical reflectance spectrum, but the amplitude of the reflectance is so low that it's only been done for like one planet ever, and even that at fairly moderate significance. And so I often point people to this and say experiments from the lab are showing us that the planets might be brown. Okay. So a couple more JWST results that are very new are some of the first direct measurements of cloud composition. So I showed you all of this evidence for clouds. There was tons of modeling done, demographic study to try to understand what the clouds and hazes actually are. And finally, thanks to JWST, we can actually see it directly. And so one example here is WASP 117, spectrum of a hot Jupiter shown on the left. You can see an absorption feature from solid SiO2, so solid quartz, right between 8 and 9 microns. The shape and amplitude of this feature is very sensitive to the particle size. So the inference here is that these are small particles, about 0.01 microns, so really small, at high altitudes, less than a millibar in pressure. And then another example of this is a hot Neptune, WASP 107b. The spectrum is shown on the right. And there isn't quite so much of a slam dunk spectral feature from the cloud, but there is an overall broad trend in the opacity that you can see with that yellow opacity source that's shaping the spectrum is some type of silicate. With the quality of the data, they can't tell exactly which one, whether it's anything between MgSiO3 to SiO, hard to tell, but one of those absorbers has to be in there to explain the overall shape of the spectrum. So this is again brand new. Both of these results are from last year. And so I think this opens a new window into studying cloud chemistry and exoplanet atmospheres that we never had access to before. Okay. Good. So I have a little over half an hour left. I'm going to quickly get some water because I'm losing my voice, and then I'm going to come back and talk a little bit about rocky planets. I'll be right back. All right. Hope everybody's hanging in there. I see one thing in the chat. Is that something that could be answered now, or better to wait until the end?
No, just thank you message.
Okay. Good, thank you. Yeah, I can't actually, I see that there is something in the chat, but I can't read it. Okay, good. So I saved the most fun part for the end. I want to talk a little bit about rocky planet atmospheres, where we stand, what we're looking for, what prospects are for the future. So, a couple of questions I'd like to address. One is, same as before, what are our expectations? What do we think rocky planet atmospheres should look like? Which ones can we observe and what have we learned so far? Moving ahead, what is a biosignature? How are we actually hoping to identify signs of life on a rocky exoplanet? And finally, what are the prospects for actually detecting those biosignatures? So, expectations. This is much more difficult for rocky planets than it is for gas giants. And that's because the atmospheres of rocky planets are shaped by a much greater diversity of processes. And we can see evidence for this in the solar system. So here's Mercury, Venus, Earth, and Mars. Very different atmospheres for these 4 planets. Mercury has essentially no atmosphere. Venus has a very thick carbon dioxide dominated atmosphere. Earth has a atmosphere made mostly out of nitrogen with now a good amount of oxygen, trace amounts of CO2, of water. And finally, Mars has a little bit of an atmosphere that's mostly made out of CO2. And a big open question for planetary science is still, how did these atmospheres get to be this way? Where did they come from? How did they evolve? Some of the factors that are important are the delivery of volatiles during the formation of the planet. So what was it born with? How much carbon, nitrogen, oxygen did it have? How much was outgassed by volcanic activity? So atmosphere interior exchange is really important. How much of the atmosphere was lost over time? We think that Mars may have once had a thicker atmosphere that could have been blasted off by a giant impact. Most of the atmosphere was lost. Venus could have once had water, but went through a runaway greenhouse and was left with only CO2 predominantly remaining. So all of these things, initial delivery of volatiles, atmosphere interior exchange, atmospheric evolution through loss either by impacts or photoevaporation, all of these factors are really important. And it is very difficult to predict a priori what type of atmosphere a rocky planet will have, or even whether it has an atmosphere at all. But we can still learn a little bit. So one very first question is just looking at the masses and radii of the planets. What can we learn from that? And the short answer is that we have learned that these small rocky planets do not have hydrogen-dominated atmospheres. You can see from this mass radius diagram here that below about 1.6 Earth radii, so the smaller planets, all of these are well fit by a rocky interior composition where the planet's radius is dominated by its core and its mantle, so the iron and silicate material. Any atmosphere on top of that has to be very thin. So for reference, Earth's atmosphere and Venus's atmosphere, those are so thin that the additional radius of the planet is negligible for typical precision that we have for exoplanets. If you start putting hydrogen on the planet, it increases the radius so dramatically. So even if you put 1% of your mass, of your total mass in hydrogen, that more than doubles the radius of your planet. And so those planets do exist. So those are the kind of 2 to 3 Earth radius planets coming in at 5 to 10 Earth masses. But those are not rocky planets, sort of by definition. If you have a thick hydrogen atmosphere, you're much more akin to a Neptune than you are to an Earth. And final point on this, if you could say, oh, suppose you just have a teeny tiny amount of hydrogen, less than like 0.1% by mass. Technically, that's possible, but those atmospheres are extremely vulnerable to atmospheric escape. So it's really easy to lose one of these super thin hydrogen atmospheres. And so you have to have a very finely tuned scenario where maybe you have a little bit of outgassing of hydrogen from volcanic activity tuned at the exact perfect rate so that you don't blow up your planet into a mini Neptune, but enough to balance the loss. And so that is just too finely tuned of a scenario. And it's much easier to explain the planets as having these rocky cores, either with no atmosphere or a thick, high mean molecular weight atmosphere on top, not a hydrogen-rich atmosphere. Okay. So what could these high mean molecular weight atmospheres be? Here's a great regime diagram from Tim Lichtenberg in a recent review paper where he looks at what we might expect for rocky planet atmospheres as a function of planet size and temperature, increasing temperature from right to left, increasing planet mass from bottom to top. And you can see that for, I'll start actually with the habitable zone, so near Earth. You would expect for rocky planets with comparable insulation to Earth, you would expect nitrogen, you'd expect water, you'd expect CO2 and CO. As you go colder, you have CO2 collapse, you're left over with nitrogen and methane or CO. An example of that is Titan in the solar system. It has a methane-dominated atmosphere. Cool off again, and you get collapse of even N2, that gives you Pluto. On the other end, as you push towards the hotter side, you'd experience a runaway greenhouse, and you would expect carbon dioxide, you could expect nitrogen. It's really easy to get oxygen in these atmospheres, but abiotically. And this happens because water molecules, as you heat them up, they can photolize into oxygen and the hydrogen is light and escapes to space, and you're left over with a lot of oxygen that could accumulate to hundreds of bars of oxygen. And so oxygen alone is not a good biosignature because it can very easily accumulate from abiotic processes. So this is a rough guide, but like I said in the last couple of slides, rocky planet atmospheres are very complicated, and so this is really only for illustration and not to better for illustration than for prediction, I would say. Here's a brief summary of all of the important physics that can shape the atmosphere, everything from escape. We've learned from giant planets that photochemistry is important, hazes, condensation, atmosphere interior exchange, circulation, cold trapping, atmospheric collapse, impacts, all of these things and more are shaping what your atmosphere could possibly be. And so my job as an observer is to just go out and look at some of these things. With all respect to my theorist colleagues, there's only so far you can go with theoretical models. And we got to just get some data to test some of these ideas and see what we can actually learn about rocky planets beyond the solar system. And so far, almost all of the focus has been on rocky planets orbiting small M-dwarf stars, and this is purely for convenience. So this has been called at times the M-dwarf opportunity, and it has many different parts. So one big one is that most of the stars in the galaxy are these smaller M-dwarf stars. They're simply just way more numerous. Not only that, but the habitable zone of planets is closer in to these cooler M-dwarf stars. So planets in the habitable zone are much more likely to transit statistically. And finally, this goes without saying, but if you're measuring transits of the planet, the bigger the planet is relative to the star, the easier it is to characterize the planet's atmosphere. And to illustrate this, on the right-hand side of the slide, I have to scale an Earth-sized rocky planet relative to an M dwarf like TRAPPIST-1 compared to a star like the Sun. And you can see that compared to an M dwarf, the rocky planet it's decent. It's big enough where you can really see it. And compared to a Sun-like star, these rocky planets are just so small that it's very, very difficult to impossible to actually characterize them with current facilities, even JWST. So there's been a lot of effort in the last 8 or 9 years to measure spectra of rocky planets orbiting M dwarfs. Here are 2 of the first spectra for planets in the TRAPPIST system. I expect many of you are familiar with TRAPPIST. This is the system of 7 transiting rocky planets orbiting a very nearby ultra-cool dwarf star that's roughly the same size as Jupiter. And TRAPPIST-1 provides still the best opportunity to characterize many rocky planets all in the same system. Here's the first spectra, though, and they were featureless. They were flat. They were able to rule out hydrogen-dominated atmospheres, which we didn't expect anyway, but they were still consistent with higher mean molecular weight. They were consistent with clouds, and they were also consistent with no atmosphere at all. And so building up over subsequent years, this is the complete sample of rocky planets that had been characterized up until 2022. And all of these planets, the result was the same. There were no features detected. Solar composition atmospheres were very strongly ruled out. But all of these other possibilities, having a heavier atmosphere, having a cloudy atmosphere, having no atmosphere, all of those were still possible. So what else can we do? Because this is a huge open question. We really want to know the answer. And I was impatient. And so I was thinking, what other way could we use to characterize some of these planets? And one of the things we can do is, rather than measure a transmission spectrum, we can instead measure a phase curve or a secondary eclipse to measure the heat redistribution on the planet. The thicker the atmosphere is, the more efficiently it redistributes heat from the day side to the night side. And so if you have a very thick atmosphere like Venus, the day side and the night side are close to the same temperature, even though one side is permanently irradiated by the star and the other side is dark. If you have such a thick atmosphere, it very efficiently redistributes that heat around to the night side. By contrast, if you have a bare rock, all of that incident stellar light lands on the day side of the planet, where it is absorbed by the rock and re-radiated back to space. So there's no heat transport at all from day side to night side. And so for a bare rock, you have a maximum temperature contrast between the 2 hemispheres. So very excitingly, about 5 years ago, my personal favorite planet, LHS 3844b, was discovered by the TESS mission. This planet is in some ways totally representative of this population of rocky planets orbiting M dwarfs. It is about 30% larger than the Earth, orbiting a small M dwarf 15 parsecs away. What makes it special is that it has a really short orbital period of just 11 hours. So equilibrium temperature is about 1,000 Kelvin, which was hot enough to potentially observe with Spitzer. So this is all pre-JWST. So I got super excited, proposed for a really ambitious Spitzer program. This was 100 hours in the last 6 months of Spitzer's life. We got the time. This is what we measured. So this is the phase curve of LHS 3844b. Do you think it has an atmosphere? I can't see you, so I'm going to assume you're thinking. Everybody's thinking. So a couple of things to note about this phase curve. So you can see that as the planet's day side rotates into view from left to right, you get this very sharp increase in brightness. Then the planet is eclipsed by the star. The night side temperature that you can infer from this is very close to 0. So the fact that the phase variation amplitude is about the same as the secondary eclipse depth means that by the time you get to the night side, it goes all the way back down to 0. The phase curve is symmetric. You might see with your eye a little bit of structure, like those few points before the secondary eclipse look a little bit low. That's consistent with white Gaussian noise, so that's your eye playing tricks on you. There's no significant signal there. So all of this put together is looking like super bad news for this planet's atmosphere. Does the planet have an atmosphere? No. It is so dark, and this is a big cartoon no, but it's coming from very extensive theoretical modeling, that there's no atmosphere that you can put on the planet that would allow you to have such a high temperature on the day side. And in fact, the temperature is so high that we know that the rock has to be very dark, similar to basalt, fresh basalt that you would get from volcanic eruptions. Here's a picture of me and my husband. We were on vacation and got to see Mount Etna in Sicily. And I thought this was super cool because this is perhaps similar to the exact type of rock that we're seeing on the surface of LHS 3844b. Here's the data point that we measured compared to some rocky surface models. So here are a couple of different types of rock spectra compared to our data point. That's the black cross. And you can see that the best fit rock composition is this blue basalt model, which is similar to the lunar mare or the surface of Mercury. You can get this type of composition if you have widespread volcanic eruptions that cover the surface in lava and then cools into this dark black rock. Okay, so that brings us up to 2022. And for the last part of the lecture, I want to talk to you about what we have learned from JWST, which, as usual, has been a total game changer. So, there's a couple of different ways to do this, and I thought the most fun way would be to give you my personal opinion, because the results are coming out really quickly. They were still in the interpretation stage, but I'm here. I have you as a captive audience, and so I want to give you my editorial, my own opinion about how likely it is that the planets we've studied so far have atmospheres or not. So I created a very scientific tool called an atmospherometer, which I'm going to use to rank the planets that have so far been observed with JWST. Okay, here we go. So first look, we're coming back to the TRAPPIST-1 system. This remains the single best system for studying the atmospheres of multiple rocky planets orbiting the same star. The first observations focused on the innermost planets, so B and C. If you push farther out, E, F, and G are potentially in the habitable zone. But the hotter the planet is, the easier it is to study. So we started with B and C. This is the secondary eclipse of TRAPPIST-1b measured with the MIRI instrument at 15 microns. And this reminds me so much of the very first hot Jupiter thermal emission measurements, where it's like a single photometric band. You detect it, but not at the highest significance. You can see clearly there's a drop in brightness near orbital phase of 0.5. That's when the planet's going behind the star. But it's, we're still just at the very, very earliest days of making these measurements. So what does this actually mean for the planet? Here it is. So this is the, you can see the measured 15 micron flux compared to a couple of different models. You can see a Venus-like model in the turquoise color. You can see and there's a big absorption feature from CO2 centered at 15 microns. That was why this wavelength was picked for this observation. But the planet is way hotter than you would expect for a CO2 dominated atmosphere. In fact, it matches almost exactly with this prediction for a planet that is as hot as possible, which is exactly what we found for the first planet we looked at with Spitzer. And what that means is very bad news for the atmosphere. So we think this one is most likely, based on what we know today, most likely to be a bare rock. Okay, so in a certain sense, that is not so surprising. It's about 500 Kelvin, so that's pretty hot. And that motivates pushing to colder temperatures where perhaps an atmosphere is more likely to survive. So moving on to planet C. This is work led by a grad student in my group, Sebastian Ziba. Sebastian got a job, so I should update this slide. But here's the same thing. So this is the measured thermal emission from the planet at 15 microns, compared to a couple of different models. And you can see that in this case, the planet is a little bit cooler than the as hot as possible line. So it's cooler at about the 2 sigma level. It's not as cold as you would expect if you had a big CO2 absorption feature here. So you can see in a thick atmosphere with CO2, you get a model spectrum represented by the red line. If you do an exact Venus analog, you get the yellow line. So we're still seeing higher temperatures than that. But it's not quite as hot as TRAPPIST-1b. And so in my atmosphere, my very scientific atmospherometer rating, I'm going to give this one, I'll skip that, a 6.2 out of 10. There's still some hope for this planet. Of course, to confirm this, we need both higher precision data and broader wavelength coverage, and that is coming with additional JWST programs. This planet is going to be observed a whole bunch more, and that should give us a definitive answer whether or not an atmosphere is present, and that would give us a basis to try to determine what the chemical composition is if there is some atmosphere there. Okay, here's another exciting one. But don't get too excited yet. So this is the first rocky planet that was observed in transmission. And you can see that there is a small feature present that as you push towards the bluer wavelengths, there is a small increase in flux. And this is really exciting, but should also be interpreted somewhat cautiously, because you could explain this feature with an atmosphere present on the planet that has some water vapor. So the blue model is a planet atmosphere with water vapor. But you could also explain this with water vapor in the star's atmosphere. This star is cold enough that you get water in its photosphere, and it's very difficult to distinguish between water in the transmission spectrum of a planet versus water in an unocculted star spot. So, oh yeah, here's an actual Doppler imaging reconstruction of what a stellar photosphere could look like. You could see in this case that there's polar spots that are quite a bit cooler than the effective temperature of the star. You can have water vapor forming in those spots. And so it's really not clear which one of these we're seeing. And we're going to need broader wavelength coverage to break the degeneracy between these two models. So I'm agnostic about this one. I'm saying this is a 5 out of 10. The star is on notice. We need some more data to confirm, but still exciting possibility. Here's another one. So this is also a small rocky planet orbiting an M dwarf. And on the left-hand side, you can see in the first visit, the measured spectrum was pretty similar to what I showed on the last slide. You see this small increase in transit depth, potentially due to water absorption. But in this case, the proposing team got 2 observations of the planet. And in the second observation, that feature goes away. And so that was very worrying because we don't expect the planet atmosphere to be varying on this timescale or at this magnitude. But the star spots totally could be because the star is rotating, the star spots are rotating in and out of view. And so this was very, very concerning that the feature vanished on second observation. So this one, I'm holding out a little bit of hope, but honestly, if I had to bet money on it, I would say most likely there's no atmosphere here, and instead we're seeing a feature from the star. And finally, I also wanted to show an example of TRAPPIST-1b, which is the first planet JWST measured for thermal emission. And if you remember, that is the one that I said is slam dunk. This one is a bare rock. But actually, in the transmission spectrum, you still see these features. And so this is also very strong evidence that there's some type of stellar contamination that is driving these features rather than something from the planet. So my rating for TRAPPIST-1b is 0 out of 10. Oh, come on. This one is, we already had the thermal emission with the hot day side showing most likely no atmosphere here. Okay, so here's our scorecard. We just started. So you should take all this with a grain of salt. These are my personal opinions based on the rapid pace of measurements that has come out in the last year. In total, we have 2 cases where it's pretty clear there's no atmosphere. We have 3 where I'm pretty worried about the star contaminating the spectrum, and we have 1 case where there's a hint of an atmosphere that needs to be followed up. So this is interesting already, though. I mean, we've got 6 planets, and one takeaway that I think is a strong one is that if all of the planets had thick atmospheres, we would know that by now. So either only some of them do, or relatively few, or even none of them do. I think that's the first takeaway. And we're just at the beginning, right? So there are dozens more observations that are scheduled. This is a question that we will answer in the next 5 to 10 years. How common are these atmospheres? If any of the planets do have atmospheres, how far can we push it? What can we actually learn about the composition of those atmospheres? And in particular, can we search for biosignatures already with JWST? So first, what are we actually looking for? A couple of quick words about what biosignatures are. The key idea behind a biosignature is that it is disequilibrium chemistry in the atmosphere caused by biologic activity, not other types of disequilibrium. So no vertical mixing, no photochemistry, no atmosphere interior exchange, no outgassing. This is caused by life and only by life. On the Earth, the classic biosignature pair is the simultaneous presence of oxygen and methane. Oxygen is produced by photosynthesis, methane is produced by bacteria, and in chemical equilibrium, we expect those molecules to very quickly react with each other and form other byproducts. But the fact that on Earth we see both of those molecules together is a really strong indication that there's something very unusual going on with our atmospheric chemistry. So oxygen and methane is the classic biosignature pair, but there are also others that have been proposed. So there's methane and CO2, pH3 has been proposed as a biosignature, oxygen, collisionally induced absorption with other molecules. These are some of the ideas. And so a big question is, here's an example. This is what Earth's transmission spectrum would look like. So you can see the oxygen A band, you see ozone, you've got water, methane, CO2, and CH4. And so this is the starting guess for what we could hope to see in a rocky planet atmosphere. Of course, it's not necessarily exactly like Earth. I get asked this a lot, why are you so focused on oxygen? It doesn't have to be oxygen, but this is a place to start. How far can we get with JWST? So I already showed you that, it's going to be a process. We still don't know if any of these planets even have atmospheres or not. But for the most favorable cases, it should be possible to detect some of these biosignature pairs. So here's kind of a best case scenario. This is TRAPPIST-1e, which is one of the easiest, maybe the easiest habitable zone planet to characterize. And here's what the possible methane and CO2 biosignature pair could look like. And you could detect both of these. If you don't have clouds that are too thick, you could add together something like 5 to 10 transits to build up enough of a signal to detect these. Of course, you have to be able to correct for any features due to the star. The star is not going to have methane and the star is not going to have CO2, so it's not as much of an issue for these as it is for water. But it is possible, perhaps, for a very small number of cases, for very, very best cases. That said, for me, that's not good enough, and I think that's true across the field. JWST is going to be great at telling us how common atmospheres are at all on rocky planets orbiting M-dwarf stars. So that's a big question. It's a focused one. JWST will answer it in the next 5 to 10 years. But it doesn't quite get us all the way to biosignatures, and it also doesn't get us, at least not for a significant number of planets, and it also does not get us to rocky planets orbiting sun-like stars, so true Earth analogs. JWST doesn't get us to there. So in the last couple of minutes, I wanted to just give a broad look to the future, what we can expect with the next generation of telescopes, both on the ground and in space. So starting from the ground, the ELT, which will be the first of the 30-meter class telescopes in operation, will be capable of taking pictures of rocky planets. This will be the first direct images of temperate Earth-sized planets. This is a simulated detection this is a bit of a cherry-picked example. This is a simulated detection of a rocky planet orbiting Alpha Centauri A. I think we already know there is no such planet like this. But the expectation is that the METIS instrument on the ELT will provide, for perhaps not quite as clear as this, but will provide the first detection of a directly imaged rocky planet. It may be possible, if we are very lucky and work very hard, to detect molecular oxygen from the ground at very high spectral resolution by searching for the change in the Doppler shift of the planet as it orbits its star, with the caveat that in order to detect this signal, we have to correct for the effects of Earth's atmosphere orders of magnitude better than we currently do. So I think this is really the challenge for the next 10 years of ground-based observations, is to see how far we can push on getting as much out of the data as possible. The photons in principle are there if we can find them. So this is also exciting, but still not really, really we want, we're scientists, we want a sample of 100 planets where we can really get good spectra for true Earth analogs to search for biosignatures. And that is the goal of the next generation of space-based observatories. So one of these is the Habitable Worlds Observatory. This is a US-led mission with large contributions from international partners. It was identified as the top priority for astronomy in the 2020 Decadal Survey. The goal would be to build a space telescope with 6.5 or 6+ meter diameter and a coronagraph that would be capable of observing the habitable zones around 100 nearby stars to measure spectra of those planets. This is a huge effort that is kicking off now. Some of you may have heard of the START team. START is an acronym that I cannot remember now, but the goal is to design the mission, look at technical feasibility, incorporate what we're learning from JWST to make this the mission that we want, to actually measure spectra for a sample of something like 25 rocky planets in the habitable zones of sun-like stars. At the same time, and this is my last slide, so we'll have time for questions, there's also a parallel effort in Europe called LIFE, which is a very ambitious mission design infrared interferometers flying in formation that will operate at the mid-infrared wavelength range to measure thermal emission spectra from a sample of over 100 rocky exoplanet atmospheres. And this is very complementary to HWO, which would provide optical reflectance spectra. This would be the mid-infrared counterpart. And Sasha Kwanz at ETH Zurich is the person who's leading this. And I think this needs support from the European community to ensure that it flies. So for me here in Germany, this is an exciting future focus. And that is all I have to say. We have about 15 minutes for questions. Thank you so much for your attention. This is a long time of me talking at you. I think we have a very bright future ahead for studying the chemistry of exoplanet atmospheres from gas giants all the way to Earth analogs. And I'm happy to use these last couple of minutes to take your questions. Thank you.
Thank you, Laura, for this very beautiful, excellent lecture. So we are coming to questions. So everybody is encouraged now to ask questions in chat. And we are starting now with already questions which are here. So the first question, water is the most important molecules for life. We are looking for water or some other molecules for the chemical and biological evolution of planets.
That is a good question. And I think future lectures will probably cover this better than I will. I would be thrilled just to detect water. We know that water is a really important solvent for chemical reactions. Everywhere on Earth where we find water, we also find life. Where there's no water, we find no life. So I would say first follow the water, and then anything else we could get on top of that, so much the better.
Yes, thank you. So the next question, perhaps I missed something, but how did you do FIR with just one data point? So it was probably to some of your point of presentation.
Yeah, I don't remember exactly.
If you could.
That might have been for searching for the atmosphere on the rocky planet with just one point.
Yeah.
Yeah, that's a good question. When you can measure, you can't learn the chemical composition with only one data point, but you can measure the temperature. And if you measure a very hot temperature on the day side of the planet, you know that you're not circulating heat. You know that you're not seeing any absorption feature that would be caused by an atmosphere. You know that you're not seeing any cloud that would also decrease the temperature. And so the short answer is, if you measure a hot temperature, it's almost certainly a rock. If you measure a cold temperature, that could have a number of different interpretations that you'd need additional wavelengths to follow up.
Okay, actually here there is a clarification in the chat. So it was not about FIR, but a feed with just one data point. Okay.
Yeah, so okay, a fit. So if I only have one data point, what I typically do is compare to like model prediction. So rather than doing the fit, Instead, I would look at like a grid of model predictions with reasonable assumptions and see how that compares to the data point. I think that's we argue about this a lot. I think this is a really good question. But I would say when you only have one data point, it's a good time to really lean on your theorist friends for what they might expect the atmospheres to look like.
Okay, thank you. So we are going to the next question. How do you select the offset when using transmission spectroscopy?
That's a mean question. This is a difficult. So in case not everyone is familiar with this, it can be difficult to calibrate the absolute transit depth of your planet when you're measuring a transmission spectrum. And so in practice, what I try to do is make a couple of different assumptions about the data analysis and see what the range is. And you can use that range in your theoretical modeling of the atmosphere as you can use it as a prior for how much of an offset there might be between different wavelength ranges.
Okay, thank you. So the next question, is there any range of plausible albedo values for a habitable planet? And about planets with albedo of 0, what do you think? What are they made of?
Yeah, so Earth's albedo is about 0.3, and that's driven predominantly from our patchy cloud coverage. A habitable planet does not necessarily need to have clouds like Earth, though, and so I would say we don't, you could have a higher albedo, you could have a lower albedo. Except for the very, very lowest albedo, like what we're measuring for some of these rocky planets, where they are as dark as possible, that points towards a very, very dark rock, like basalt, that is absorbing almost all of the incident stellar light.
Okay, thank you. The next question, could there be some chemical signatures in atmosphere of an exoplanet that would indicate presence of the planetary magnetic fields?
That is a super awesome question, and the short answer is no, not really. There have been some other approaches to searching for magnetic effects, including star-planet interaction. If for the very, very closest transiting planets, the magnetic field of the planet could actually have an effect on the star. There have been some radio searches for aurorae, but at our level of precision, there's no information about the atmosphere we can get that will tell us much about the magnetic field. And unfortunately, that would be super cool if we could.
Okay, thank you. The next question is again about the magnetic field. Does an atmosphere require the planet to have a magnetic field?
That is also a good question. I mean, my understanding is that a magnetic field is supposed to help keep an atmosphere, but I don't know if it's absolutely required. I'm not sure if anyone knows that. I think it's still an open question.
Okay, thank you. The next question, what are the major physical factors that determine the formation of atmosphere on a rocky planets? Could this type of knowledge help to narrow down the searching regime?
Yeah, there are a lot of different factors that shape whether a rocky planet has an atmosphere or not. Everything from how it formed, so how much ice it formed with, the cooling history of the interior, plate tectonics, volcanic activity, atmospheric escape, atmospheric erosion and loss. So all of those factors have big uncertainties in the modeling about exactly what we should expect. And in practice, there aren't actually so many rocky planets that we can reach with our telescopes. And so what I always say is beggars can't be choosers, because there's only so many, there's only a handful of planets that we can really do this for. And so I don't want to narrow our search regime too much in advance, because there's so many uncertainties in the theoretical models. So I think we should look at everything we can look at and use that as our guide.
Okay, thank you. So I also want to ask one question. So in your observation, it looks like you don't observe too much atmospheres on the rocky planets. So, but is it because it's a general property of exoplanets, or is it because you're focusing or can observe only those exoplanets which presumably shouldn't have those atmosphere?
We don't know yet. That's a good question. Yeah, so I didn't get a chance to talk about this, but the rocky planets orbiting the smallest stars might have the most trouble keeping an atmosphere, because the smaller stars are more active. They take a longer time to contract to the main sequence, and so they're really bright in the ultraviolet for a very long time. And that can photo evaporate a lot of atmosphere from these planets. So it is possible that they're less likely to have atmospheres at all. But I also think it's true that it's still really early days and that we have a lot of observations still to do. So we just barely started looking. So I wouldn't give up just yet.
Okay, thank you, Laura, very much. I think our time is approaching already to 5, and I think, yeah, we should probably already stop. Maybe if you still have time, there is a last question in chat now. Would atmosphere be more likely in planets with more collisions with asteroids?
Ooh, I actually think the atmosphere would be less likely if you have collision with a big asteroid. If it's big enough, the asteroid can like blast off the entire atmosphere and you lose it. So I think that, I mean, maybe if you had a smaller one, there's not enough, the amount of like extra ices that you could get from, say, a comet is not enough to offset the amount of atmosphere you would lose from such a giant impact.
Okay, thank you. I think, yeah. As I don't see more questions, so let's thank you, our lecturer, for this beautiful, perfect lecture.
Thank you very
So
much.
thank
It was a
you,
pleasure.
Laura, a lot. Yes. And I finish this lecture today, and have a still nice day.
You too. Have a good day, everybody. Thank you for the questions. Thank you for hanging in there for almost 2 hours. It's a long lecture. And yeah, I wish you all the best with your studies and your scientific career. And if you have any questions, feel free to shoot me an email.
Thank you. Thank you.